students, in last class we have talked about a thing called electric dipole. So, we will quickly revise what we have done in the last class, then we will proceed further. So, in last class we defined a thing as electric dipole. Electric dipole is basically two equal and opposite charge separated by a distance is called as electric dipole. So, you have two charges, magnitude of both the charges are equal, but the nature of the charges are opposite. One charge is positive, one charge is negative. So, this thing is called as a dipole. Now, for a dipole we defined a quantity called dipole moment. We have defined dipole moment whose magnitude is q into 2d. So, here q is the magnitude of one of the charge and 2d is the distance between the charge. So, simply dipole moment is charge into distance between the charge. Then we have said that this dipole moment is a vector quantity and the direction of this vector is from negative charge to positive charge. So, direction of electric dipole will be in this direction. So, from negative to positive. So, this we have defined as a dipole moment. Remember, dipole moment we have written the magnitude only, but it is a vector quantity. Direction is from negative to positive. Next thing was we have found out the electric field due to a dipole. So, suppose you have a minus charge here and there is a plus charge here. Then we have found out electric field at three different places or two different places at this point and at this point. Here and here magnitude and direction of the electric field is equal. So, this point is on the axis. So, here electric field magnitude was E is equals to 2 kp by r cube. So, at this point the magnitude of electric field is 2 kp by r cube, direction of electric field is along the dipole. So, here the dipole is in this direction, so electric field will also be in this direction. Similarly, here also electric field is 2 kp by r cube and direction is again along the dipole. So, here also the direction is same. So, remember, on the axis of the dipole, on the both the side of the dipole, the direction of electric field remains same, which is along the dipole moment. At this point the magnitude of electric field was kp by r cube and the direction is opposite to the dipole. So, dipole is in this direction, electric field will be in this direction. So, this is the electric field due to a dipole. Next thing we have done is potential due to a dipole. Potential due to dipole at the axis. Here the electric potential will be kp by r square. Here, as the point is close to the positive charge, so the sign of the potential will be positive. Here potential will be minus kp by r square. As you know, potential is a scalar quantity, so sign matters. So, here the potential is kp by r cube, here potential is minus kp by r square. So, if the question asks you electric field is same at both the points, yes, electric field here and electric field here is same. Why? Because the magnitude and direction are equal. So, at this point and at this point electric field is same, but at this point and this point potential is different. Here potential is positive, here potential is negative. Similarly, at this point potential was 0. As we can see, this point is equidistant from both the charges. So, here potential due to this will be negative, potential due to this one will be positive and both of them will cancel each other out. So, net potential at this point will be 0. So, you have to memorize these things. On the axis electric field and potential, at this point which is close to the minus charge electric field and potential, and at the perpendicular bisector electric field and potential. Again remember, for a dipole electric field is directly proportional to r cube and electric potential is directly proportional to 1 upon r square. For a normal charge electric field is directly proportional to 1 upon r square, for a potential is directly proportional to 1 upon r. So, till this point we have done in the last class. Next thing we are going to do is electric dipole in an external electric field. So next heading is dipole in external electric field. So as we know that electric field can be uniform or it can be non-uniform. So we are going to study this in two different headings. First one will be in uniform electric field. So in last class we have also said what is the uniform electric field. Uniform electric field means a electric field whose magnitude and direction both are constant, and representation of uniform electric field is like this. We draw parallel lines, we draw straight parallel lines whose distance are equidistant. Now, so this is the uniform electric field, and in this uniform electric field I have placed a dipole. So this charge is plus q and this charge is minus q. So we are going to study electric dipole in a uniform external electric field. So external electric field is uniform, which means the magnitude and direction of electric field is constant, and in that one we have kept a dipole. This charge is positive, this charge is negative. The direction of dipole is this. Now we are going to talk about the force on this dipole. Now as we have seen in the earlier classes that the force on a charge in the electric field can be written as F is equals to Q into E. So force on a charge in external electric field can be written as Q into E, where Q is the charge, E is the electric field. If charge is positive, force and electric field will be in the same direction. If the charge is negative, force and electric field will be in the opposite direction. So here this charge is positive, so magnitude of the force on this charge will be Q into E and the direction will be along the electric field. So here direction of electric force is in this direction, which is Q into E. So magnitude of the force on this charge is Q into E, direction of this force is along the electric field. Similarly, the magnitude of the force on this charge will be Q into E, but the direction will be opposite to the electric field. As we know that electric field here is in this direction, so the force on this charge will be in this direction, and the magnitude of the force will be Q into E. So on a positive charge, force in the direction of the electric field. On a negative charge, force is the opposite to the electric field. Now if I ask you what is the net force on this dipole, net force on this dipole will be 0, because this force and this force, both of them have same magnitude, but direction of the force is opposite. So net force on the electric field will be, net force on the dipole will be 0. So remember this thing, if you place a electric dipole in a external uniform electric field, net force on this dipole will be 0. Now let us talk about the torque on the dipole. Torque can be written as R cross F. Now don't make this mistake that this is F net, this is only F. F net is 0, but F is not 0. There is force on this particle, there is force on this particle, both of them will add up in, because they are in the opposite direction. So net force will be 0, but F is not 0. I hope you remember from your class 11 what is torque, definition of torque. Now, so torque is written as R cross F, or you can write this thing as, the magnitude of torque can be written as Rf sin theta, where R is the distance of the point where the force is applied, F is the force, and theta is the angle between the R and F. So suppose this dipole moment is in this direction, electric field is in this direction, and this angle is theta. So the angle between electric field and dipole moment is theta. Now, so this angle will also be theta. Now if I want to find the torque, I have to find the torque due to this force and torque due to this force. Now torque this force will be 0, as we know that this force is passing through this point. So I am finding the torque of these two forces about this point. So about this point, torque of this point will be 0. So net torque I can write, due to this force it will be 0. Due to this one I can write R, which R is distance. R, remember R is the distance between the point and R is the distance between the point where the force is applied and the point about which you are finding the dipole torque. So we know that this distance is 2d. So here I can write this distance, R is 2d, force is Q into E, and the angle between these two is theta. So I can write this thing as 2d sin theta. Again From here I can write Q into 2D as P. So net torque, tau net is P E sin theta. So this is the magnitude of the torque. Now if I want to find the direction of the torque, as you can see here, this will be A, this will be B, this will be sin theta. So this can be written as A cross B. So torque in the vector form will be P cross E. Again, net force on a dipole in a uniform electric field is 0 because both the forces have same magnitude, direction is opposite, so net force will be 0. Next thing is torque. As we know that torque is R cross F and both the forces are acting in the different points, so there will be torque, so this dipole will rotate. How do you know that there will be torque? Because if you apply the force in this direction and this direction, you can see that this dipole will rotate like this. So torque on the dipole can be written as P cross E, which can be written as P E sin theta, where P is the magnitude of the dipole moment, E is the magnitude of the electric field, and theta is the angle between the dipole moment and electric field. So you have to remember these two things. Net force is 0, torque is P cross E or P E sin theta. So now that we have seen the force on the dipole and we have seen the torque on the dipole, now let's talk about the potential energy of the dipole in external uniform electric field. So we know that potential energy, so the change in potential energy can be written as work done by external force. Here net force is 0, but there is torque. So here the work done by external agent will be opposite to the torque applied by the electric field. So work done can be written as integration of tau dot d theta. Just like you can write the work done by a force is F dot dr. Similarly, work done by a torque is tau dot d theta. This is your basic mechanics from your class 11. Now from here delta U can be written as integration torque. We just now seen it. It will be P E sin theta d theta from theta initial to theta final. Again P, as the electric field is uniform, so P and E both are constant, but theta is changing. So I can take these two outside. The integration of sin theta d theta will be minus cos theta. So delta U can be written as minus of P E cos theta from theta initial to theta final, which can again be written as minus of P E cos theta final minus of P E cos theta initial. Again if you compare this one and this one, this is delta U, which is U final minus U initial. So this is the U final, which is the final potential energy, this is the initial potential energy. So from here I can write the potential energy is minus P E cos theta. So this is the potential energy of dipole in external electric field. Now again this A B cos theta can be written as A dot B. So I can write U as minus of P dot E. So now we have seen three things for a dipole in uniform electric field. First thing is force. Net force on a dipole is 0. Second, this potential energy, second thing was torque. Torque can be written as P cross E or P E sin theta, where P is the magnitude of the dipole moment, E is the magnitude of the electric field, and theta is the angle between P and E. Next thing we have seen is potential energy of a dipole in a uniform electric field. Potential energy can be written as minus P E cos theta. Again P is the dipole moment, E is the electric field, and theta is the angle between them. So this is A B cos theta, which can be written as P dot E. So here it will be P dot E can be written as P E cos theta. In a uniform electric field, net force is 0, the torque is P cross E, and the potential energy is minus of P dot E. So these are the things which you have to remember. Net force 0, torque and potential energy. Change in potential energy can be written as final potential energy minus initial potential energy. If you want, delta U is equals to U final minus U initial, which is the work done by external force, which is equals to minus of work done by conservative force. Here the work done is due to torque, because net force is 0, but there is torque on the dipole. Second thing we are going to talk about is dipole in non-uniform electric field. Now, as the name says, the non-uniform electric field means the direction is also opposite, so direction is also changing, or magnitude is changing, or both of them are changing. So if you place, suppose the dipole electric field is like this, and you are placing a dipole like this. This is minus q charge, this is plus q charge. As the electric field is non-uniform, the magnitude of electric field here and magnitude of electric field here is different. So on this point the force will be along this direction, which I can write q into E1. At this point the force will be suppose along this direction, which will be q into E2. So as we can see, magnitude wise both the forces are different and direction of both the forces are also different. So net force will not be 0. So that's all you have to remember. In a non-uniform electric field, net force on a dipole is not 0. Again I will repeat, you don't need to worry about what will be the force, you just need to remember in a non-uniform electric field F net on the dipole is 0, simple. So net force on this dipole is 0. Now let us find out the torque. Torque, again we know that torque can be found out about any other point, any of the point. About this point, if I want to find the torque, I can write the torque of this will be 0, but there will be torque of this point. Now torque of this point I can write, torque of this point can be written as P E sin theta. Theta is the angle between P and E. As we know that the angle between P and E can be 0, it can be non-zero. So from here the torque can be 0, it can be non-zero. So here again you have to just remember the result, what is the net torque. So net torque may be 0, may not be 0. Again, two simple results which you have to memorize. They are not going to ask you what is the magnitude of the force, and they are not going to ask you what is the magnitude of the torque. But just remember, in a non-uniform electric field, net force will always be going to be 0, and torque, it may be 0 if both electric field and dipole are in the same direction, it will be 0. When it will be non-zero, when there is some angle between electric field and the dipole. So torque may be 0 or may not be 0, but force will always be non-zero. In a uniform electric field, net force is always 0, torque again may be 0, it may not be 0. That we have seen, torque is P cross E, which is P E sin theta. If theta is 0, torque will be 0, if theta is non-zero, torque will be non-zero. So torque, it may be 0, it may not be 0, but in case of uniform electric field, net force will be 0, in case of non-uniform electric field, it will be non-zero. Now with this we are done with the topic of we are done with the topic of dipole. Now as your from your exam point of view, this topic in whole electrostatics, this point is very important, because you can expect at least one question from this topic. lot of students have confusion in this topic, because here electric field is 1 upon r cube, potential is 1 upon r square. So remember this thing and revise this thing again and again. You can expect at least one question from this topic. Either and the question will be very simple, either they will ask you the variation of electric field, or they can ask you the direct formula for electric field, or they are going to ask you what is the net force on the dipole, what is the torque on the dipole, or what is the potential energy of the dipole. From your exam point of view, very important, very easy, but confusing. So revise this thing again and again. Now we are going to start a new topic, which is electric field and potential due to continuous charge distribution. So next topic is electric field and electric potential due to continuous charge distribution. Till now we have found out the electric field due to a point charge. We also have found out the electric field due to a electric potential due to a point charge. Due to a point charge, electric field magnitude can be written as kq by r square. Potential can be written as kq by r. So this is due to a point charge. Similarly, electric field due to a dipole can be written as kp by r cube on the perpendicular bisector. So this will be perpendicular bisector. On the axis it will be 2 kp by r cube. Similarly, on the perpendicular bisector, potential will be 0. Potential on the axis close to the positive charge, it will be kp by r square, and close to the negative charge, it will be minus kp by r square. So this is for. So we have found out the electric field and potential due to one single point charge. We have found out the electric field and potential due to 2 point charges, which is also called as dipole, where one charge is positive, one charge is negative. Now we are going to find out electric field and potential due to continuous charge distribution. Continuous charge distribution means the charge is distributed over either a length, or it is over distributed over a surface, or it is distributed over a volume. So according to that, we can define 3 kind of charge density. First will be linear charge density. Linear charge density, which is a symbol for that we are going to use as lambda. So suppose you have a length. On this length there is charge distribution. Charge is given to this as q, total length is L. So on this I can take a very small element. On that small element the charge will be dq and length will be dl. So here charge density is defined as lambda is equals to dq by dl, where dq is very small charge element and this is the dq is the charge on the small element, dl is the length of the small element. From here, if charge density is uniform, this can be written as simply q divided by L. So if charge density is uniform, you have to use this relationship. If charge density is uniform, you have to use this lambda is equals to q by L. So this is the linear charge density. Second is surface charge density. Surface charge density symbol we are going to use as sigma. Here the charge is distributed over a surface. So you have a surface, total area of the surface is A, charge given to this surface is Q, and I take a very small element on this one, the element area is dA, charge on this one will be dQ. So from here surface charge density can be written as dQ by dA. Again, if surface charge density is uniform, then it can be written as Q by A. So for a length we define linear charge density, which is lambda. For a surface we define surface charge density, which is sigma. Simple relationship which we have seen in your mechanics also. We have seen linear mass density, we have seen surface mass density, and we have seen volume mass density, which we simply call as density. Similarly, there is volume charge density. For volume charge density, we are going to use symbol as rho. So you have a volume, total volume is V, charge given to this one is Q. I can take very small volume dV, on this dV small charge will be dQ. So from here I can write volume charge density will be dQ by dV, which is equals to Q by V. Here remember, this V is the volume, not the potential. So rho is equals to dQ by dV, where dV is very small volume element, dQ is the small charge on that small volume element. If rho is constant, then the charge density can be written as Q by V. So for a linear charge density, for a linear object we define linear charge density. For a surface object we define the surface charge density, and for a volume object which has a volume we define the volume charge density. Now that we have seen electric field due to point charges, we have seen the electric field due to dipole. Now we are going to see the electric field and potential due to a uniformly charged rod. So what do you mean by a uniformly charged rod? You have a rod and the length of this rod is L, and the charge given to this rod is Q, and this charge is uniformly distributed over this rod. And I want to find electric field at a distance A from this end. There is a point P, at this point P I want to find the electric field, I want to find the potential. Again you have a uniformly charged rod, length of this rod is L, charge on this rod is Q. From this end there is a point, there is a distance A, there is a point P, at this point P I want to find electric field and electric potential. Now I cannot write electric field due to this rod, here will be kq by a square, because this is not a point charge, here charge is distributed over the length. So what we need to do, we have to break this into very small point, then we are going to assume each point as point charge, and then we are going to find the total electric field here. So what I am going to do is, I am going to break this into very small distance dx. So length of this very small point is dx, and charge on this one will be dq. So from here I can define linear charge density as dq by dx, which can be written as q divided by L. If linear charge density of this one is dq by dx, as this is uniform, I can write this thing as q by L. Now due to this dq, I can take this separately. So this, there is a charge dq, due to this dq charge at a distance x, there is a point P. At a distance x, there is a point P where I need to find the electric field. Due to this very small charge, the electric field will be very small, so I can write dE is equals to k dq by x square. Here small charge is q at a distance x, electric field will be kq by r square. Here k is k, dq is this, and x is the distance between the charge and the point. So here due to this very small point charge, the electric field will be k dq by x square. If I want to find the total electric field, I just need to do the integration of this term. So I can write total electric field will be integration of k dq by x square. From here dq can be written as lambda into dx. So this can be written as integration k lambda dx divided by x square. Now here I have to decide the limit of this integration. Limit will be, as you can see, x, minimum value of x will be from this point to this point, which is a. So minimum is a, maximum distance is a to a plus l. So this will be a plus l. So the total integration will be integration k lambda dx divided by x square from a to a plus l. Now as k and lambda both are constant, I can take it outside. So this integration will be 1 upon x square, integration will be minus 1 upon x. So I can write this thing as total electric field k lambda minus 1 upon x from a to a plus l. From this I will get E is equals to k lambda 1 upon a minus 1 upon a plus l. Again if I simplify this further, I will get E is equals to k lambda divided by a into a plus l. This will be a plus l minus a, which will be l. Again lambda into l can be written as q. So I can write this thing as kq divided by a into a plus l. So this is the electric field due to that rod. So electric field due to a rod on the axis, the point is at a distance a from one of the end. So electric field can be written as kq divided by a into a plus l. The direction of electric field, if the charge is positive, will be away from the rod, and if the charge is negative, it will be towards the rod. Next we are going to find out the electric potential. The approach will again be same. As the charge is not a point charge, we are going to divide this into very small point charges, then we are going to do the integration. So you have a rod, length of the rod is L, distance charge on the rod is Q. At a distance A, there is a point P. You want to find the potential here now. Again I am going to divide this into very small charges. I can assume this is dq, length is dx. For this point charge, the distance between this point charge and this distance is x. So very small potential can be written as k dq by x. Again dq can be written as lambda into dx. So total very small charge is lambda into dx. So total potential can be written as integration of k lambda dx divided by x. Integration limit will be from a to a plus l. Again k and lambda are constant, I can take them outside. So this integration will turn out to be k lambda ln x. As you know, integration of 1 upon x is ln x. Limit is from a to a plus l. So from here, total potential can be written as k lambda ln a plus l divided by a. So electric field is k q divided, again lambda can be written as q by l. So electric field is k q divided by a into a plus l. Potential is k lambda ln a plus l divided by a. Again remember, this is for a rod whose length is L and charge on this rod is Q, and we are finding electric field and potential at a distance a from the one of the end. So here we have found out the electric field and potential. So finally you have to remember this thing. You don't need to remember the derivation. This derivation is not in your NEET exam also, the derivation is not for your board exam also. It's finally just remember this result, and from your exam point of view, frankly this is not that important. This is just for your practice, so you can find out the electric field due to various charge distribution, because later part of the in the later part of the chapters we have to find the electric field due to various charge distribution. So this is for your practice. there is no harm in memorizing this thing. You can memorize this thing, but for exam point of view, this one is not that important. For your practice, just memorize this thing. So that's it for today. Quickly I will summarize what we have done till now. We have done electric dipole in external electric field. Electric field can be uniform, it can be non-uniform. In uniform electric field, net force is 0, torque may be 0, it may not be 0. In a non-uniform electric field, net force will not be 0, torque again may be 0, it may not be 0. Then we have found out the electric field due to various charge distribution. We have seen electric field and potential due to uniformly charged body, one is rod. In the next class, we are going to find out the electric field due to a uniformly charged ring. After that, we are going to move on to the next section of the chapter, which is electrostatics 2, where we are going to find out how you can find electric field very easily without using the integration. As you can see, we have used integration here, which is very difficult to, for NEET student, it is very difficult to take care of the integration. So we are going to see how you can find the electric field and electric potential without using too much of integration. Till then, my advice to you is revise again and again, because this chapter is the basic of your whole class 12th. So revise as many times as you can, because you have time right now, so you can revise it as many times as you can. Till then, keep revising, and I will see you in the next class.